PhD for the presentation. So I'm indeed an architect and researcher. And I will try to share the work we did in the critical zone at mapping observatories. So it's mostly observatory, not to see the sky or the stars, but to see the Earth and also underneath Earth. So this is a book, Terraforma, just to briefly introduce, and our practice, both as a collective, SOC, and as a landscape architecture design studio. And we work a lot with different disciplines. It's actually why we developed first this practice to do mapping at the intersection between art, science, and architecture. Working with Frédéric Aïtouati, for example, who is a historian of sciences, or Bruno Latour. We have been in long collaboration with him. And I actually started to work on critical zones as an architect with scientists of the Earth studying environmental issues. So this is this work I will try to present and to discuss some mappings using an alternative systems. Reference system, sorry. So here, critical zones mean really critical environments. Our planet has indeed become a critical zone in the sense that habitable conditions are deteriorating. A number of Earth scientists are monitoring this transformation, for example, the shortage of water, or the pollution in the air, or the soil disappearing, etc. So you know very well the issue at stake. And the question I wish to discuss are the following. So at the time of the Anthropocene, how can we trace a world in movement and unstable Earth? And how are new emerging sciences, the critical zones, renewing our understanding of nature? Scientists alert they are not always listened to, and Bruno Latour, philosopher and sociologist of sciences, dedicated his whole life to make the scientists be heard by politics, society, citizens, and various practitioners. So following his path, and after having the chance to work with him, we continue this interdisciplinary work with scientists, architects, social scientists gathered in critical zone observatories. So what is this critical zone for Earth scientists? According to their definition, the critical zone is a habitable part of the Earth between the rocks and the sky, a few meters above and below ground, as a cut section through the Earth. And this zone is critical because this is where we live, actually, where we grow our food and pump our water, as well as where we excavated the Earth to build. So the term captures the urgency of the habitable condition because it's impacted by human activity. It's a zone under pressure, and this zone is studied in observatories around the world. So here you have the two networks, the OSCAR, this is a French network, and the Critical Zone Network in the US, who coined the term and who first developed this observatory. Just a zoom. And so an observatory is a site, a landscape, often a watershed, which is chosen as a sentinel of environmental disturbances, and where different scientists measure water, soil, air, organisms, and their interactions. So these are very highly instrumented places with sensors to monitor a very wide range of environmental issues, and they use geophysics, geochemistry, biology, hydrology, and so on. And there are kind of similarities between architectural practices or field practices, actually, or art practices. We are on site too with various disciplines, and often in ruin landscapes to understand their composition. But I think there is maybe earth science and designers don't often work together, and sometimes we project also design before understanding nature, its composition. So as an architect, I found interesting to to rely on these scientists before starting a project to understand this issue and generally what is called the Anthropocene. But first, what led me to the critical zone was a cartographic problem submitted to me by the scientists themselves who faced a big issue. The critical zone is not visible at the scale of the Earth. When we see the Earth from above, we cannot see this thin pellicule of the critical zone. At this scale, it's not visible. I will show the little animation. When we zoom in, it's actually the scale of the critical zone at the scale of the globe. So it seemed that we needed a cartographic frame capable of situating us in the critical zone. So with Jérôme Gaillardet, a scientist, critical zonist, we propose an alternative mapping system. We reverse the classical referential. We turn the Earth inside out, so to speak, and we place the atmosphere in the center and the rocks at the periphery and the core, the mantle, far away. And we wish to, with this view, to give a better understanding of the soil and more space, and also to give depth to our mapping system. In this way also, what is in the atmosphere don't escape in the infinite universe, but is trapped inside planet boundaries. And the rocks are actually our limit. So contrary to the view of the planet floating in the universe, the pollution that we release into the air doesn't escape, but is trapped into these atmospheric layers. But actually, there is also another understanding of this representation, is that we also have biochemical cycles, and soil alter, weather, erode. And this is also what this representation want to do in a more sensitive way. So to have this closure of the Earth, but also this recycling, this cycle, which actually make the Earth habitable. So you see just some scheme diagrams of the same representation. But in order to draw the maps of the critical zone, it's necessary to go into the fieldwork and to explore the critical zone from the inside, to find what is on observatories and what are the findings of the scientists working in there. So the following map I will present are made for and from the critical zone observatories, and I will try to detail 2, maybe 3 or 4. We will see how it goes. So what the field consists of? So it consists of following science very closely, where they are in their observatories, how they use the sensors, what they measure, how it changes the way we understand what the landscape is, because some measure consist of taking samples from the soil or the water, or to install tiny devices on site for a long time. But some of our sensors are also more perennial in the forest, for example, under the trees. And some of our sensors are also very high-tech, such as the River Lab that will appear on the screen, which is a real lab put into a landscape. And inside, there is a machine recording the chemical composition of the river each 20 minutes, and all the chemicals. So it's very interesting because it gives you a molecular view of what is a river, and it's actually more than we think of. It's not only water, but there is also a flow of calcium, a flow of phosphorus, a flow of also chemical input. So it's interesting as it demultiplies the view of the river. So the critical zone, although a well-defined research program, is also an unknown zone. unknown to other disciplines and non-experts, but also to the scientists themselves who are seeking to understand its dynamics. So they continually develop and create new sensors. And what we did on the field that we use an alternative map, the one I presented, to collect what we found. But yeah, let's take an example and go into a well-equipped critical zone observatory in the Vosges forest. So we made a little animation. So here is the location of the critical zone observatory. It's near French-German border. These are the limits of the watershed. And then we made another kind of animation to understand how we reverse this soil surface. And we put, again, the atmosphere at the center. And when we go more peripheral to the maps, more we go deep into the soil. And here until 100 meters. And what we've done now is to map each instrumentation one by one. So it will appear. So it is the model. And then we have the station. And the first station is a geophones. It's actually geophysics. It probes the soil deep underground to understand the composition of this soil, if it's porous or not, if the rocks are compact, etc., and to understand how the soil is weathered. And so they put vibration on the ground with a hammer, and they record this vibration, the sound actually of the soil. It's interesting, and it's technique hijacked by from oil prospection. So it's also interesting how the scientists hijack this instrument. These are the weather station. A more conventional one with temperature input, rain, snow cover, and it records how some chemicals can come under the Vosges forest in less than 20 days under certain conditions. So coming from ASEAN, especially the sulfur emissions, they come in 20 days on this forest, and it causes acid rain, an issue which was very important in the 80s, and it has been partially resolved, but there is still a lag in the soil here, and they are still very acidic, and especially because it's a spruce forest. So forests grow because of industries to harvest wood, and so it contributes to acidify the soil again. The trees are also monitored, especially the fruit fall when rain pass under the leaves, and they try to understand how the tree resorbs some pollution or how nutrients pass through the tree and then into the soil, and to understand how is the forest resilient or not. And it's also interesting because it's like there is a mirroring atmosphere in the depth. There's CO2, they have water, the gases. So it's like a mirror, and I think it's nice. And this is a gravimeter station. So this is a more high-tech one, very expensive actually. And it monitors the gravity of the Earth. And also the very tiny signal of the hydrological signal of the water table at depth. And this instrument is very sensitive, so it can record the echoes of the tidal waves hundreds of kilometers away. So it gives you also an understanding of the connectedness of the Earth and how this underground vibration that could be in the rocks. And these are a more conventional technique or core sample, which would consist of taking out rocks from the depth, and they can see how the rock is fractured, that is, how the rock being porous and sound, and where the water is passing through these rocks. Because it's a granitic formation, so it's like very compact, but whereas like fracture, and it's very difficult to understand where the water is passing. It's not like a porous zone; it's very water path. We don't really know where they are. These observatories is also there is the sources, which is the water for the village downstream. So the water of these sources are also monitored, and they have different temperatures depending on the way they are going through the deep rocks or not. So the more you are depth, the more it's hot. And finally, the river station that I already told you about, with the monitoring of the composition of the chemical composition of each flow of water. And so it's with the superimposition of these sensors that we can build this map, because we have to take data from elsewhere. We are not relying on conventional satellite imageries. And so we need this view for the sensors to be able to gather it and to try to map these observatories. But as Jennifer Gabri's, a scholar in media studies, argue in her book Program Earth, it's necessary to bypass an automatic understanding of sensors as detecting environmental data, as if there is a world out there with phenomena to be made visible. Instead, she argues, sensors actually concretize different environments, different milieus. That is, they enable particular environments to materialize. We've explored this watershed I just presented in the map very extensively, and we recreated in a museum at the ZKM in Germany as part of the Critical Zone exhibition curated by Latour and Webel in 2020. And we produced actually an architectural model to the scale of the instruments. So we can not see the landscape with the traditional element, but it's revealed through the different stations that we have seen in the map. So just to see a few images, and we had also some videos from artist Sonia Levy. Now I will try to present a map from a new project called Gaia-graphic, and it's part of a project called Terraforma Equipex. So it's not, it's the same name as a book, actually, because the scientific program borrowed the title, but it's not a book. And it's a project aiming at designing and testing in situ observatories sensors. So they develop new sensors coupling different viewpoints, some humans, biotic or abiotic, and it's connected. They try to be low-tech, and what they actually want to do is to give these sensors to citizens. So it's a kind of scientific participatory science. So there are different sensors like material flow sensors, carbon tracers, nitrate tracers, GPS collars, microbial activity monitoring sensors, etc. And they choose 3 pilot sites to develop these sensors. It's called the implementation phase, because there are 3 different landscapes, very different, with very different critical environment. a mountain ecosystem in the Alps, a coastal ecosystem in Brittany, and an agricultural landscape in Occitanie in the south of France. And what the scientists ask me is to to map these three observatories with the sensors they already have, but also the sensor that will be developed in the Terraforma project. So I will try to present at least one map. We'll see if we have time for the three of them, but maybe I will just show them. So this is the location of the observatory in the coastline. And actually, coastline are very critical environments because of sea level rise, but also because of salt water, which may contaminate fresh water underneath. And the urban pressure on coastlines also threatens water resources. And what is also interesting and is little known in the underground is that water path at depth may contribute to the development of microlives, microorganisms in the subterranean. So that's why also this map is called subterranean microlives. So I'm going to read some extracts from the field with the map. On the site, Elliot and Camille, the geochemist, lower the probe into the well, which spits out a rusty, slimy substance that comes out with the water. This water, which may be older than we are, comes from a few hundred meters deep in the rocks and has seen this fossilized mineral world for a brief moment on the Earth timescale. Scientists record microbial activity in the underground world. There is a striking contrast between instruments that are barely visible on the surface and the richness and proliferation of what they can show us of the world below. There's nothing on the surface and everything is happening beneath our feet, hidden from our view. We become aware of the intense reactivity underneath through the lens of an artesian well filled with biofilm, a colored, vibrant material in the water, or through the discharge of a very particular rust-colored water on the surface because it rises from the iron-laden depth, all clues to an intensity down there. In the world above, we also feel the intensity of gaseous reactions in the air, rapidly changing weather, volatile clouds, ocean mist, micro-humidity quickly swept away by air currents. An impression of hovering, elusive flow, in any case difficult to capture and materialize. In the lab, the images shown to me by the scientists confirm this feeling of the field. Hot, cold, temperature logs, electricity and pulsations in the soil. I hear very little about stability, but rather about fractures, where reactive things happen and connect. And then the living chemistry of the underground environment, fragile and robust at the same time, and the contact zone created by the collision of two rock movements, a long cycle resulting in the formation of breaks, fractures, small elements, and particles ejected at the surface. At the same time, but moving in the opposite direction from the surface, water and gases also infiltrate below, further contributing to the dissolution or disintegration of the rock. But while the surface may seem stable, the environment underground is reactive, even radioactive. These gases, like radon, an ancient element of the Earth's crust, released by the gigantic crash that took place, or hydrogen or helium, are undetectable by the senses. They have no smell, no color. So how can we visualize them? How can we give them an existence, given the extent to which they condition the trajectories of an environment? The second map is the observatory in the south of France, an agricultural scenario very different from the previous. Beneath this green fields blanket, a well-kept cover of rotating crops, lies a very different story indeed. Turned over, plowed and washed away, the blanket is far from a smooth surface with no scratches or holes. Patched up, mended through its wounded pores, sip and escape the agent of its downfall, nitrates. In the map of Orade, this observatory where agricultural practices are monitored, the map is structured around agricultural cycles, so seasons. Unlike the other map, which was structured around different environments. We have here a more seasonal map, actually. And in the depth of the soil, we try to show the alternating of sandstone, clay and limestone in the geological bedrock, which are characteristic of molasse from the ancient Pyrenean landscapes, and whose sediments continue to erode under the effect of agricultural practices. So here soil loss is shown on the map by the fining of the brown layer on the hills. And here the question is, how can we make visible what is disappearing? The soil eroding, but also the insects dying out or the birds no longer returning. An environment where practices are slow to change and to halt these disappearances. To name a few of the entities which are represented here, so the Pyrenees, the Garonne River Valley, the seedlings, the farmers, the rainfall, the molasse, the paleo rivers, the groundwater, the surface runoff, the paleo roots, CO2, flux towers, flux eddies, piezometers, next bost, connected feeder, birds, bees, etc., etc. Consequently, maybe the critical zone expands our understanding of nature in a more diverse and complex way. There are more entities, heterogeneous and multiple, that compose an environment, and their activity actually terraforms the Earth. This understanding could be called a cosmopolitical one, in contrast of the anthropocentric view of nature, which is centered on humans. Here, the cosmopolitical way of understanding nature may bring into the foreground, into visibility, non-human agency that we should take into account when designing a project, for example. Maybe if I have time, just briefly to show the last observatory, which is located in the mountain, in the Alps in France. And here the meadows are covered in vivid colors, starting with red alga, gradually replacing the intense green of the grasses. The fragile microfauna of the snow-covered valleys, helping each other to survive, is replaced by species from milder environments that swear by competition. As degrees are lost at each plateau altitude, this loss is compensated by the increase in degrees from year to year, gradually consuming the iced world from below. In a reversed movement, as the mountain melts, it slides, torrents, and carries sediments. This loss is not compensated by the vast, deep uplift of the tectonic below, inaccessible Stonian worlds, far too slow to keep pace with the world above. How can we make visible what is felt by living things, also known as the bioclimate? In an environment that is constantly changing to the rhythm of melting and snowing and accelerating. Other cartographic reference systems are those needed to bring the variables together. The challenge is to make the discovery of one group of another or another commensurable, to integrate different questions, different concepts and governance, and to generate new research questions. For example, as we can see, how can we map something that is disappearing, the soil erosion, or how to map what we do not yet know, like the underground microorganisms. This is a different instrument that the scientists used in these observatories, so to make a little focus on them. And we also map the phenomena bring into visibility with this instrument, as well as the plants here, which are very important because here in this observatory, they look at biodiversity, biology, and also the DNA in the soil. And actually, this little microfauna is disappearing because snow melting has a different course than before. So it's an environment changing. So we still think that the mountains are something very big and not so easily to move, but actually there is a contrast between this tiny fauna and this Stonian world monster of geology. What we try to do also is to bring a kind of commensurability between the different sensors that the scientists use, and to follow a bit our way, we try to give credit to visualization, but also body to visualization. In short, so yes, Harway proposes to recover vision in Cyborg Manifesto. And we try in this project, in Terraformat project, to give the feeling of the sensors also an extension of our senses, offering a new point of view through their presence also at the heart of the system. So how can we articulate these body sensors, scribers, and technical sensors in terms of continuity with our body, our extension, or complementarity, or contradiction, also maybe either. So how can the sensor extend a body that is already sensitive, already a sensors? So this is a kind of relationship. It's very interesting, I think, to address. And so inside this scientific program, I gather my contribution to this project in a website that you can see here. So you will find more stories about each map and also explaining the beginning of the project, the methodology used, the fieldwork, but also the workshops we did after with the scientists to increase the understanding of the map and to detail them. And so I will wrap it up and finish. And in conclusion, and to follow John Dewey, he said that an inquiry starts when there is a state of uncertainty, of unknown, or trouble, also to quote Haraway, and may end when the tension is released. If the inquiry in the critical zone is underway, I think it's certainly not over, and we still have to learn how to coexist with the geo and bio entities that compose the Earth. And we hope to renew our understanding of nature in order to grasp the cosmologies of the beings and the elements which are terraforming the Earth's habitability. Thank you for your attention.